what is the situation? We have two random variables, x and y, which are continuous. Now, the first thing that we have to know is that when the two random variables are continuous, the probability model is given by the joint density. And the joint density is really a very big thing and very, very important. But in practice, you're not going to have two random variables only. You're going to have more than two random variables. And finding the joint density, even if you have sometimes two random variables, and things are quite complicated, can prove to be a very difficult task, actually. So what we do is to resort to less information, and that's exactly the concept of linear regression. Okay? Now, what is this? Before seeing what is the less information, I need to tell you, I need to give you, for example, give you some example or illustrate the concept a little bit. The joint density, if we have two random variables, x and y take real values, so both of them take real values. That is a function of x and y. So here, so far you have seen density functions with one independent random variable, which independent random variable is defined within the range of the random variable. So here you have independent variables x and y, whose values are taken from the range of values of x and y. So you will see here on the right hand side a formula that has two random variables. For example, it can be this. I'll give you an example right now. It's 1 over 2p e to the negative x squared plus y squared over 2. Actually, this is a very beautiful function, and it's a normal distribution. This is one example of the bivariate normal distribution. So when we would say that x and y here, the pair, has a bivariate normal distribution. We'll talk about this model more later on. But we will not talk a lot about this model. We'll talk very restrictively, in a very restricted sense about this model. But here, that's one example of a joint density. When we have a joint density, we can have the marginals. And this is basically what I'm going to tell you, what the marginals are, because I need them to define the conditionals and what is the covariance as well. So the marginal of x, that essentially serves as the density of x. But it's not precise to say here is the density of x, here is the density of y. And it's not precise because they may have interaction. The way one random variable takes its values may influence the way the other random variable takes its values, and this is what we will be talking about today. So the marginal of x is defined as an integral from negative infinity to infinity of the joint density, where now you integrate only with respect to the second variable. Okay, so that's the variable quantity, and that's the fixed, and actually this fixed quantity turns out to be exactly equal to this. Okay? So if I want to find, in other words, what does this formula tell me? If I want to find the value of the marginal density of x at a given point value of the random variable x, namely this one, take the joint density, fix x to be that particular value that you have in the left-hand side, and take the integral after you have fixed x by letting y run throughout the range of y. Now that's single integration. So what would that amount here? It would amount to fixing x and integrating here with respect to y only. And that's an integration that is not, that's actually quite easy here. If you see, let me do it. So that's my immediate application. I write the square root, I write 2p as the square root squared, and you will see why I'm doing this. Once I put dy inside here, this value is fixed, and it's actually equal to this value. So what I will do is that I will use the laws of powers of numbers. I will split the exponential in two parts. Do you agree, first of all, for my algebra?
Yes.
Do you find it easy, my algebra? Or do you find it difficult? I don't want you to feel uncomfortable today, not because I'm particularly good, but because that meant to be an easy talk today, an easy lecture. I want to keep it like that, so that you can grasp the main meaning. So is my algebra clear, how I move from here to here? All right? Now, as I said, this is fixed. So all of these quantities that I have here are fixed. They don't change. Their value doesn't change. So this is a constant. That's how it should be treated inside the integral. And the constant will be pulled in front of the integral. And if you pull it in front of the integral, then you will have this. And inside the integral, you will be left with the other part, the square root of 2p, e to the negative y squared over 2 dy. And what is this function here inside the integral? No, it is the density of the standard normal. That's what I want precisely to hear. That's the density of the standard normal. It's a density function, so if you integrate it from negative infinity to infinity, you find the terrific value 1. So overall, all this product will give you e to the negative x squared over 2. So here, when I started with this example of the density, I found that the marginal of x is exactly the density, the value of the density function of the standard normal distribution at this particular lowercase x. So here you see an example of the marginal. Likewise, I can calculate the marginal of y. Now, this time, I fix y inside the integration and let x vary. So this is fixed. And it's the same as this one outside. So this is the marginal of y. Okay. Now, if the joint density is such that it happens to be the product to split in, to be factorized in this way, essentially be given as the product of each of the marginals, then what we say is that x and y are independent random variables, and we have seen this with discrete random variables as well. So the definition of independence remains exactly the same regardless of what the random variable is, or what the random variables are, to be more precise, okay? Now, what happens if they are not independent? Well, when they're not independent, there is interaction with the two. And essentially, the concept of linear regression is a concept where, as we say, we find the conditional distribution of one random variable with respect to the other. And the linear regression started as a way of essentially linearizing the interaction between two random variables which are normally distributed. And here there is a very beautiful result, actually, that I want to talk about, and I want you to learn about it in less mathematically and more in a sort of a general Discovery Channel type of fashion. Right, so what is the density? What is the conditional? The conditional is saying, suppose that you have an information. Let's say, let's do it with y. Suppose that you have an information that the first random variable, lowercase x, receives this value. What is the distribution of y if we know that the first random variable has locked in this value? This is again a density, so this is here the conditional density. Density of y given, that's very, very important, given that x has assumed a certain value. Right? Now, you've seen this before many times in your labs. Suppose that you do an experiment and you try to prove experimentally Ohm's law. So you have a resistance, a thermal resistance, whose value is R, and then you start changing the intensity of the current, or you can as well change the voltage at the ends of the resistance, and you measure with an instrument.
In order to make experiments, what do you have to be saying on a line?
What? You measure with an experiment.
Resistance is the only thing that we can directly measure, right?
Well, you can, when you apply Ohm's law, you can measure all of those quantities, okay? You can measure I, R, and resistance. And an instrument that does this is a polymeter. The polymeter can measure all three, give you all these three measurements, okay? The polymeter will not give you inductive resistance per se, will give you the mixed resistance. Inductive, capacitor, and thermal, all together, okay? But if you turn it only into the direct current mode, then you will only see the thermal resistance, which is this R. And Ohm's law basically tells you that I is equal to U divided by R. That's a very basic law that we teach when we first start physics. And of course, here you know that U is the voltage difference is R times I. So if I know, let me put I here. If I know I and I know U, then I can set the value of I and measure the voltage. And if you do this, and I believe you've done this in the lab, you will get those points by changing different values of I, and you call that scatter plot, correct? So here you have a scatter plot. Why does this scatter plot appear? Well, it appears because you have two random variables. Here, your random variables are I and U. You will tell me, I set the value of I. Why is I random? Well, it is random because the value that you've set is not going to be exactly the value that is being applied. There are errors. And you don't know much about these errors. And therefore, if you don't know about much of these errors, you can say these errors are kind of random. All right? And that actually makes, had there been no errors, everything would have been perfectly on a straight line. Since there are errors, you don't have a straight line, but you have values, points, data points up and down the straight line. So sort of the straight line lies in the middle of the scatter plot, in the middle of the point cloud. Now, what I'm saying here is that the first random variable, which is my intensity, so I will call it cap I from now on to indicate that it's random, has taken a value, let's say, equal to I sub 0. Well, if you do the, how do you've done this in physics, -101, correct? How do you find the voltage? After you have drawn the line, and you probably have taken 3 or 4 points of initial measurements to draw the line, then you take the vertical up here. It hits this diagonal, almost diagonal line at this point, then you take the vertical to the other axis, and you say this is the U sub 0 value.
Wouldn't voltage be the independent variable and current the dependent variable?
I will go to that. The way we've said it, yes, this is independent, this is dependent. And exactly this kind of, I wouldn't call it causal relation, because you see, when you say one variable is dependent on another variable which is independent, but not in the concept I spoke before, then you imply some causality. In this case, there is causality. But in the context of linear regression that I want to talk about, there is no causality, or causality cannot be established. You see that two things change at the same time as one changes, the other changes. So one changes influences the other change. But you can't say the reason for which U changes is the change of I. That's what the law is telling you. The deterministic part of the law is actually talking about this causal relationship. But if this were not voltage and intensity, which I used here, but there were basically, let's say, let's do something else. Let's put here income, total days of incarceration. I switch to a social study. Is there any law that you know that tells you, here is your income, those are your total days of incarceration, here is your income, those are your total days of incarceration?
No.
There's none. None of it. Okay? And of course, if you put Bernie Madoff, actually would be very to the right, he has many days of incarceration. So what's going on here? But there is no, essentially, how would you do this? Well, you would say average income and average days of incarceration. So you will go to a population that you target, and you say, well, you classify them based on their average income and report their average days of incarceration, like that. And you will get a value like this. So suppose that you get something like this. What does that mean? The curve, this curve. Would that imply that if you have low income, you certainly are likely to go to prison?
Yes.
Or you go to prison? Would you derive that result? No, of course not. It's wrong, and it's actually dummy to derive it, because deriving that result implies causality. You can imply causality simply because you see some sort of correlation of values.
On this case,
Never imply causality because you see correlation.
saying that the amount of that if you have no income, then you are more likely to spend more time in jail, it does not imply causality. Saying that because you have less income, you will spend more time in jail does. In this case, the evidence clearly shows that Yes, if you have an lower income, chances are you're going to spend more time in jail.
No, you can't.
It's a correlation because that's a coronary relation.
No, it's not correct. And that's basically that social, there is an expression, I think it's called social automatism or something like that. I don't have the right expression right now in my mind, so let's not that. But the point I want to make here, and I want to raise it, and that's why I picked up this example here, which is sort of grotesque if you think about it. It's socially grotesque and statistically grotesque. It's because I want to make a point, and I want to make it through that grotesque example that the fact that you see two random variables changing their values together in some sort of coordination does not imply causality. One is not the cause of the other. To establish the cause, you have to move independently of the statistics, essentially. Actually, you have to do tests for independence as well. We'll talk about this a little bit. And you have to establish mechanically, with some sort of argument, of persuasive argument, of a proof. Statistics cannot all the way through show causality. Cannot establish causality. Can give you enough indication, but cannot be the proof for causality. At the end of the day, you have to prove the causality by showing it, by establishing and saying this argument, therefore, and that happens, that leads to that. You have to explain what you observe in a persuasive argument. So causality is not something that you can derive from statistics, yet statistics are many times being extrapolated for causality. Classical example, I'll tell you one, which is actually not true. If we reduce taxes, then there will be more jobs. True, not true. Actually, not true. And the stellar example is the observation that we have for 10 years. We have the Bush tax cuts, which are deep tax cuts, and the job market is moving independently of the tax cuts. Had there been any causality?
There is causality based the other way.
Martin, had there been any causality? I'm not going to argue about that. Okay. But since you are not in a position to argue, my opinion prevails. I have ex officio the dominant position, okay? The position to, argue from the position of authority, of course. That's why you are a professor, after all. What is logical fallacy? No, but you have independence, okay? There is independence because the job market is not moving to any direction. It's slightly moving to the better direction. Therefore, had there been, since the tax cuts were deep already, the job market should have been high, but it wasn't. It actually collapsed at one point amidst of very deep tax cuts. Why? Because investment does not depend on the taxes. Essentially, it depends on the opportunity, on seizing the opportunity. Because the one who invests a lot, the one who invests a lot has already the capital that is required. The accumulation of capital exists. It's not like mom and pop's business, who will basically, I can hire one more employee if they cut my taxes by 3%. And I can cut a part-time employee who can work 10 hours a week, because that's what amounts to my tax cuts. We're not talking about that. We're talking about large scale. All right, so there is no causality that can be established through this observation. So what is this thing here if I want to go back to my example, my ohms example, which is not contestable? If you take, what do you do when you say, well, predict the value of the voltage if you know the value of I sub 0? Exactly, that's what I'm saying here. When you say predict the value, you're more or less inclined to say, well, this is the value. I'll just put the vertical here, hit this line, the regression line somewhere, and then from that point on, take the other perpendicular to the vertical axis, and that's my value. And what I'm going to tell you today, that's not correct. Or I'm not saying it's entirely incorrect, I would say it's non-precise. And here is the precise thing. When you say this is I sub 0, the value is set to I sub 0, essentially you say the first random variable logs to a value. The prediction exactly refers to what is the appropriate probability model that will govern the second random variable, namely the voltage here, given that the first random variable has locked to a value. And that's exactly the conditional density. That probability model is the conditional density. And by definition is given by this. That x is the fixed x. And here you divide by the marginal of x, which is also, so those x's all here in this formula are all fixed and all the same. So the only thing that changes, the variable thing, is this y. The left-hand side and the right-hand side. Okay? So what is linear regression? That example, by the way, is not linear regression here. So I'm going to take it out. I don't need it anymore. Actually, it set off Martin, so it was bad to begin with. So what is linear regression? Suppose that we have x and y to be normally distributed, both normally distributed random variables. Okay? Then their joint density has of what we say has a bivariate normal distribution. I don't really want to tell you exactly what the bivariate is, but how comfortable do you feel with matrices, if you see matrices? Are you all going to be okay? So I'm going to use, what? Matrices. If you see matrices, are you all going to be okay? No? How many are going to be uncomfortable if they see matrices? Only one? Hey, those are 2 by 2 matrices, by the way, because I have a 2 variable model, okay? So let me show it a little bit to you. Actually, I showed you a very easy case. The first case that I showed you here, where was it? That one here, which I took, this one. This is a very simple case of a bivariate normal distribution. Now, the only thing here is that both x and y are independent of one another. That's why, and they both have 0 mean. That's what leads to this very, very simple form. Now, in the more complicated case where they interact with each other, the model takes a slightly more elaborate case. It's 1 over 2p times the absolute value of the determinant of a matrix. This is a 2 by 2 matrix. We use the capital Greek letter sigma. And this matrix is invertible, actually. It's called covariance matrix. The covariance matrix holds the mystery of the interaction of the 2 random variables. Then here comes the elaborate part. We have 1, negative 1/2 times the following difference. X minus its mean, y minus its mean, times sigma times x minus its mean, y minus its mean. And this is a matrix product here. Okay. What you have, and this is inverse. This is the inverse matrix. Sigma to the negative 1. So that's, here we use the inverse of the covariance. This is the bivariate normal distribution in a very simple form. And it's easy to memorize because you have the matrix operation here in the exponent. However, I'm not asking you to memorize this formula, okay? I'm just mentioning it. I'm not going to need it. What is important and what is called linear regression is that if you take the conditional of y with respect to x, taking the lowercase x, then this has, it's actually a, I'm not going to write the exact formula, has normal distribution. This is the density of a normally distributed random variable. That's the important thing. And this is exactly what we call linear regression. Now, so y, as we say, when we condition any one of the two random variables, x or y, with respect to the other, the conditioned random variable has a normal distribution with mean. What is the mean? This is called the conditional mean. The conditional mean is actually the mean of x plus excuse me, it's the mean of y. The mean of y plus a coefficient here, which I would call b, times x, this value x, minus the mean of x. And this is exactly, is telling you that the conditional mean of y is given essentially as the y coordinate of a straight line, of points on a straight line. Which point of the straight line? The one that has x coordinate, the value x. And that's the coordinate here. That's exactly the coordinate. Now, what is the implication of this? It says that if you lock your value here, the mean is going to be exactly this value, this one, that I blackened, actually this one. And the values of u here, of the second random variable, will vary around this mean value. How much are they going to vary? How much are they going to vary? They are going to vary with a standard deviation that depends on how the two random variables correlate times the standard deviation of y. That you don't really need to know the formula. You just really need to know that they will vary. The variation here follows a model which is that of a normal distribution. A normal distribution with mean this value. And that's exactly linear regression. Where the name is, why does it get the name regression? First of all, why does it get the name linear? Because those conditional means, if you plot them as a function of the value x, they all follow in a straight line. They do only when you have two normal random variables. If you don't have two normal random variables, the linear regression model may not describe the entire variability. May not describe exactly fully the way how one changes with respect to the other. It will describe partially the model, but not entirely. Okay? That can happen. I can give you one distribution. I can give you x, which is normally distributed. If you take x squared, and the values of the second random variable are locked by the values of the first. Here you have causality. But those are not both normal distributed because the second one does not have a normal distribution. So the bivariate normal distribution model does not apply. The model applies fully if both random variables have normal distribution. And this is, if we really want to understand the two random variables, this is how we should start looking at them. All right? So the correlation coefficient is what determines how close they are. And actually this is rho, the correlation coefficient. I will explain what is the correlation coefficient, times sigma y divided by sigma x. And sigma y and sigma x are the marginal variances, the variances that they have themselves. So it doesn't really matter. So this b depends from the correlation coefficient. What is the correlation coefficient? The correlation coefficient is the covariance of x and y divided by the marginal standard deviation. So that's the correlation coefficient. Do you need to know this formula? Short answer is no. And my advice, which is the long answer, is you better not. Because I'm not going to ask you. The important thing is to understand what is telling you and not what the formula is. You can always Google it and find the formula. Yes? Where do you want me to pull? I didn't, where do you want me to pull it up? Like that? I didn't get it, obviously. I didn't get the request. Anyway, what is the significance of the correlation coefficient? If x and y are independent, of course the correlation coefficient is going to be 0. The opposite is not true unless x and y are both normally distributed. So when both x and y are normally distributed, to find whether they are independent or dependent, we look at the correlation coefficient. Now, if the correlation coefficient tends to be a big number, a significant number, typically greater than 0.5, then one depends on the other. That value is going in absolute value to be less than 1, less than or equal than 1. It's like a cosine. Okay, so we will do a test for correlation when we'll do the statistics part. And there you will see that we will be asking the question, is the correlation coefficient 0 or not 0? When we ask this question, implicitly we assume that both X and Y have normal distribution. If they don't have normal distribution, then the correlation coefficient cannot be reliably assessed from the statistics. We need different tests, the so-called non-parametric tests, and then we do tests for independence or not. Because if the two random variables are independent, of course, the correlation coefficient is 0, they don't interact with each other. If they are not independent, which means they are dependent, then we understand that the way one takes influences the way the other takes its values, but we don't know the exact model of the interaction. That's a different thing to know the exact model of the interaction. The entire learning theory, the entire way we humans learn, animals learn, Pavlov's dog has learned, is exactly this. So this is here the mechanism of machine learning in a nutshell. In machine learning, we know how to condition one variable with respect to the other, which means how to find the conditional expectation and how to understand or get some of partial description of the conditional distribution. We don't get all of it. What is the condition here? Oh, I thought it was my voice being recorded. So what do we know for learning? What we know for learning, what we condition is like exactly what I have here, the variable intensity of the electric current. Here it won't be the intensity of the electric current, it's going to be a data set to which I'm trained to which has been presented to me and somebody told me this is red, this is black, this is food, this is poison. Okay? That's what you are conditioned on. The inputs, and then your entire response is essentially your decision making based on your experience, and your decision making is the conditional expectation, the calculation of this value. Where of course you are conditioned, so you take decision, you do something or you don't do it. So your decisions are binary. Do or not. So essentially what you learn is how to condition your Bernoulli random variable based on the description of your training. If you are poorly trained, then you condition randomly here and poorly. Okay, what you would like here to have is if to take the right value, which would be y equal to 1, to come with a value close to 1 here. But if you come with a value which is in between, then you haven't learned properly. Your decision is going to be random and totally independent of your training. I mean, with the same head, you had no training, essentially. So in the linear regression model, we have this very beautiful relationship, and many things are basically can be expressed as linear regression models. So when we do curve fitting and many of these things, essentially we do linear, or as we call it sometimes, non-linear regression models, where here in the non-linear regression models, you don't have a polynomial of first order here because your x is at the first order. You may have also higher order terms for the x, polynomial terms. This would be non-linear regression, and you're not being taught that. A non-linear regression has one disadvantage, that you need many data points. You don't need few data points because you have more degrees of freedom essentially in the model. So you need essentially more information to be able to regress properly. Why do we call it regression? Because when you see the scatter plot, points go up, points go below the line. So you regress to the line, because when you're above and you're pulled to the line, you regress to the line. Hence the name linear regression. Okay, that's all for for two random variables. So I advise you not to look to the section in the book, but stick with my notes, the video that I've just presented to you, I'm not going to give you any problems. I'm not going to give you any uh, exercises from this, and I'm not going to examine this part in the first exam. That doesn't mean that you should not know it. Actually, you should learn it because it's very, very important to whichever discipline you will follow. It's one of the most important things I've taught you in this course. To learn, that doesn't mean that I have to obligate you by telling you, I'm going to put all of the exam out of this section. So you better know it. No. You learn it because you want to learn it. It's very, very important. All right?